Hey everybody, good morning. Good to see you guys again. Welcome back. We're about to start our lesson in just a minute, so hope you're comfortable and ready to learn a little bit more logic. And I hope you guys had a great weekend. Hey Brenna, Jamie, Rachel, Leo, Valeria, good to see everybody here. Arlene, Jessica, as usual, thanks again guys for being here. Hey one and all, good to see you guys. Thanks again for saying hello. Anybody feel free to do the same if you're here. Okay. Okay. Well, great. Good to see everyone here again. Today, we're going to continue developing our knowledge of how to do proofs. So let's see. Did any of you guys happen to notice, by the way, my message from, I think, Friday? I sent around the information for our logic tutor that we do have on campus. Can anyone let me know if you saw it? Let's see. The whole logic tutor thing. Good. Okay, yeah. So just feel free to check in with the logic tutor at all if you ever need anything. Of course, I'm here to help, and I'm always happy to do that. If you ever need any additional time or attention to any of the problems that you're working on, homework problems, preparation for exams, or anything else, definitely feel free to check in with the logic tutor. We have had her for a while. She's very good, and you know, it's just another resource for you guys to use to help you have a good, successful result. I'm pretty much done with grading your guys' midterms, and I was going to, after class today, send the announcement that starting after today, you can go ahead and just feel free to contact me through email to request your grade on that or on anything else. I want to send around an answer key for the midterm too, even though we did talk about it in our class meeting a week ago. So you can always refer back to that lecture if you want to see like the recorded version of me discussing the material on the midterm. But I want to post the answer key as well. And then anyways, you can check in with me to get your score on that or on any of the previous assignments. Homework 1 and 2, those have all been graded. That's behind us now. You could certainly check for your grades on those, but also I'm sure you want to know about the midterm. So I'm just letting you know that I'll be announcing that later today, and feel free after the announcement is sent to just check for your score. And you still have some time to work on the third homework problem set, which you're doing right now. Okay, so any questions about any of those things or anything else? Do let me know, as usual, if you have any questions, to just put them in the chat and I'll take them in real time. Okay, so as we've kind of become accustomed to, I'm going to put up the dual platforms format so that we can both share the screen and also have a good archived lecture here in the one central location on my channel. So I'm going to post the link here in just a second into our chat so that we can do the Zoom component of this meeting too. Okay, so you see there the link for this little logic practice problems session. Go ahead and launch that one. Okay, here we go. I see you guys starting to show up. Great, thanks everybody. Okay, I'm going to share the screen. Okay, got the screen sharing on. And here's our logic book. Okay. Oh yes, one more thing, the chat. Okay, everything's visible and you can hear me good? Everything? Let me know in this Zoom chat if so, just to check on our connection. All right, great, perfect, thanks. So let's just do a little review, and then I've got some new inference rules to teach you guys today. We're going to take it slow. You know, I'm not going to teach all of them all at once. I want us to build up so that we can be comfortable as we go through it, but last time we've learned just these 4 derivation rules: reiteration, conjunction elimination, conjunction introduction, and conditional elimination. So what these different rules do is they allow you to infer a new statement in a proof. When you've got a proof in logic, you are given certain number of assumptions, okay? And then you're supposed to use the assumptions plus the inference rules to derive some result, to derive some further sentence. So these rules are the rules that you use to get the derived result that you want in a proof. Okay, so let me start with these conjunction rules. Conjunction elimination, or ampersand, or in our case, sometimes caret E, that rule says that if you have a conjunction where the main connective of the statement is the conjunction symbol, you're allowed to break that down and just take one of the conjuncts off. You can take the left conjunct off or the right conjunct off. And when you do that, you'll simply write the individual conjunct that you want to strip away from the full conjunction. And then you would cite to the right in what's called the justification column the rule, conjunction elimination, the number where the conjunction was in the proof, and that's it. Conjunction elimination, line, whatever. If you want to take off the left side, you would do it as such. If you wanted to take off the right side, you do it like that. So conjunction elimination, it allows you to eliminate a conjunction and remove one of its 2 pieces, okay? Then there's conjunction introduction. With conjunction introduction, it allows you to build a conjunction, right? So it allows you to take 2 pieces, 2 different sentences on a previous lines. Yeah, you may record the lecture, but I have a private question coming in the chat, so let me just address the whole class. A student is asking me, may I record this lecture? And yes, you may, but just so that we're all clear, all the lectures are recorded throughout the whole semester, and they're all compiled on the YouTube channel where we start the meetings. So you can always go back. I mean, I'm recording lectures, and I'm leaving them up permanently. So there's no question that you can record it if you like, but in a way, it's unnecessary for you to do it because it's already being recorded on the YouTube channel. I don't know if you mean that you want to record the Zoom version of it. If so, feel free to do that, or to just record with an audio device or any other technique that you would like. I'm all about and all in favor of you having a version of a lecture that you can use later. Okay, so back to this, conjunction introduction. This is when you have 2 statements above and you want to conjoin them, put them together into a conjunction. So in that case, if you had, let's say, P and Q on 2 available lines above, you could cite the rule of conjunction introduction, ampersand I, and then you would simply list the number of the 2 lines where those previous elements occurred that you're putting together. So if it was like conjunction introduction 1 and 2, then maybe that would be the citation here. We also learned about, let me go to that in a minute, but reiteration. Reiteration just says that you can reiterate a previous statement again. So wherever you have a sentence and you want to repeat it, you can simply repeat it, but you just have to write the rule of reiteration, R, and cite the number of the line that you are repeating when you add that to the proof. Okay, and then one more, just this is still review of last week, but there was conditional elimination also. So with conditional elimination, horseshoe E or single arrow E is the label of the rule. What you do is, if you have a conditional, which says if something, then something else, right? So to the left of every conditional, let's do a bit of a quick question to you guys here. What are the 2 pieces of a conditional? The left side is called what? What's its technical name? The left half of a conditional, we call it the what? The left half of the conditional is called, let me see in the chat. What's it called? What's its name? The antecedent, very good, yes. And the right side, the other part, the part that is to the right of the connective, not the antecedent, but the other part is called the consequent. Okay, good. Now, conditional elimination is sometimes known as affirming the antecedent. That's another label that it sometimes is known by. And that is because with conditional elimination, that's what you're doing. you have a conditional, and then on a subsequent line or a previous line, you have just the antecedent of the conditional, namely the left part. So in this conditional written on the board, we have antecedent P if P, then consequent Q. So by combining a conditional with the antecedent clause, we can infer the consequent clause. So any scenario where you have both a conditional and on another line just its left part, then you can write the consequent on a next line by citing conditional elimination and the two numbers where the conditional occurs and where the antecedent occurs. Okay, so that's how we can get to the consequent of a conditional if we already have available the full stated conditional and just the left part. All right, so today then there's two more rules I would like us to try and learn. And these two rules are the rule of, the rules that you see here, disjunction introduction and biconditional elimination, okay? So let's start then with this biconditional elimination rule. I'll talk to you about this one because it is quite similar to regular conditional elimination. It's almost exactly the same. The only difference is that when you have the triple bar as the main connective, the biconditional symbol, or as you guys know, we also permit it to be the double arrow, the double facing arrow. When you have a biconditional, and then you have one of the two sides of the biconditional by itself, then you can eliminate the biconditional and get the opposite side. So if you have this structure, P, if and only if Q, and then also you have P available on one of the lines, you can then get to the result of Q, the other side. If P is true and P if and only if Q is true, Q follows from those two statements. But also with biconditional elimination, if you have P if and only if Q and you obtain the right side, Q, you can then eliminate the biconditional and get the left portion, which is P. So this is biconditional elimination, just to make it apparent in the board for those that will watch this later on YouTube. Biconditional elimination, which we can call double arrow elimination or triple bar elimination. Both are compatible and equivalent ways of citing the rule. The rule goes as you see it here. If we have P, if and only if Q, and also P, we can deduce that Q. Also, another possible application of the rule is that if we have P, if and only if, just in case, Q, and also Q, that provides us the ability to deduce P. So biconditional elimination is almost the same as conditional elimination, but here's the real difference. With regular conditional elimination, you can only eliminate from left to right. So you have to have the conditional and the antecedent. And then if you have those two pieces, you can eliminate the conditional and obtain the consequent. But with conditional elimination, you cannot do it in the opposite direction. For example, you cannot have P arrow Q, Q, and then deduce that P. That's an invalid inference. So with regular conditional elimination, you have to get the left side and the conditional, and then you'll get to obtain the right side. With biconditional elimination, though, it's symmetric. So you can eliminate from left to right or from right to left. So that's the real difference. With a biconditional elimination statement, if you have the individual sentence, which is on the right side of the connective, then you can eliminate the statement and get the left side as well. With regular conditional elimination, you can only do this left to right pattern. So when it's a single arrow, that's the symbol, we can only go from left to right by eliminating the statement or the connective. With biconditional elimination, the double arrow or the triple bar, we can go in either direction. P leads us to Q, or Q leads us to P. Okay, so that's biconditional elimination. Now, one more rule for today, and we'll save the remaining rules for the next few lessons, but I'm going to now talk to you about disjunction introduction. Okay, But maybe before I go there, I do want to make sure that we're very, very deliberate and slow. So let me try and throw out like a silly little easy proof involving this biconditional elimination. Okay, so suppose that we have, let's see here. Okay, these two statements. A, if and only if B. So that is an assumption. And suppose that we also have A and B. Okay, that's a conjunction, a second assumption. Okay, now, I'm trying to, well, probably should have made it a little more complex, because in this case, then you'll simply be able to detach one of the two conjuncts, and then that'll be your answer. All right. Well, anyway, let's just try and do it a few different ways. Derive for me, if you can, B. Let's see what your logical acumen will tell you to do in this case. So I need you to get B as a result from these two assumptions plus the inference rules. So as a proof goes, you separate the assumptions from the inferences that you draw afterward. And with each new line, you have to add a sentence and give a justification for adding the sentence. Now, what's one way to derive B here? That's quite simple. That's the goal. The goal sentence is get to B. And you have these two pieces of information plus derivation rules to use to get there. So, you know, just attempt an inference. What is some inference that you think you can make on the basis of these two statements that are premises? What can be added on line 3 is my question to you in order to get to B. Let's see here in the chat. There's only a set number of rules. You know, you see them here. So these are your options. And only a few of these rules can even apply to either of the two statements initially. Okay, so what is an inference that can be performed on either line 1 or 2 to advance this proof to the next step, line 3? Go ahead and just tell me. Okay, Evelyn, you say conjunction elimination. Very good. But in order to derive what statement? Conjunction elimination could give us what? Okay, so Leonard. Well, one answer would be quite easy, Evelyn, and I think you understand that one answer to this problem is to do this, B. And that comes from, tell me, Evelyn, please, what is the rule again and the line number? Just let me know there, Evelyn, really quick. Yes, it is conjunction elimination of line 2. Because line 2 is a conjunction. As you guys know, with conjunction elimination, we can simply remove one of the pieces, and then we would be done. But let's try another path to the same result, okay? And that's what Leo's doing. So another possibility could go in this direction. A from conjunction elimination on line 2, taking the other conjunct off. Okay, and now, how can we get to B without using conjunction elimination? How can we get to B now without using the conjunction elimination rule? Because we've now obtained A on its own individual line, which enables another rule to be applied based on everything else that's in the proof so far. So what's another route to getting this result B that we're trying to get? We only need one more step to do that, and I'm trying to show you by means of this new rule. Yes, biconditional elimination 1 and 3. Line 1 says A double arrow B. And biconditional elimination allows you, if you find one of the two sides of this, to then obtain the opposite reverse side. So since we unlocked A allows us to eliminate this biconditional, giving us B. Biconditional elimination 1 and 3. Okay? Now, so that's one possible solution to the problem, although admittedly it would have been easier to just remove one of the conjuncts there. What if I wanted you to derive A by means of a similar type of method? What could be step 3 then in the proof if the goal is not B, but rather A? Let's know about that. Another question now for this new proof problem. What could be a first step taken in line 3 to get us to A. There's two routes to it. One is a little simpler. The other one involves this rule that I'm trying to show you. But let's just see what you throw out at me. What's the inference then on line 3? These practice problems are class activities. This is not just sit back and wait for the professor to tell you. You have to think. Okay, so Frida, you're saying B from conjunction elimination of line 2. Good. B is one of the two conjuncts. We can simply remove it by conjunction elimination. But now what? We have B, and our goal is A. So what's the new inference which can close this proof in one more step, getting us to A? Okay, Valeria, very good. Biconditional elimination, well, get the numbers correct, though. Line number 1 is one of the two numbers, but what is the other number to cite? 1 and 3. Yes, that's correct. Did I? Yes, because earlier you said 2. But 3 is the line where letter B occurs. And it is these two things combined that gives us A. Okay, so I'm just showing you how biconditional elimination works. With biconditional elimination, you simply have to have a full biconditional, and then on another available line, just one of the statements on either the left or the right. And if you do, then that produces, as a consequence, the other side of the double arrow statement. Okay? Like, here, let me give you another case. Okay, so what it says here is derive the conjunction D and W. That's your goal. Get to D and W. And you have these two assumptions here. So what could be a third step of this proof? We're looking to arrive at D and W. So just tell me what's the first move that could get us somewhat closer to that ultimate goal, that derived result. On line 3, one option is to do what? Just let me know the next step. You know, just think about it. Think clearly. And there's only one clear answer that should come to you now. Because you know where we're trying to get to, and you know what we have to work with. There's a limited set of options, so you just deduce which one that needs to be done. Well, Frida, a little fast though. We can't do biconditional elimination until we first have two elements, a biconditional, and then just one thing that is on the left or the right. So ultimately, yes, we will eliminate that biconditional to get the result, but we can't do it without having the line to cite to eliminate it. So let's go. Tell me, everybody, what's the first step? Okay, so Evelyn and Leonard, A, from conjunction elimination on line 2. Okay, let's focus on why did we do that? Why did you want to remove A from line 2 using conjunction elimination? What was the point of doing that? You say to do it, good, that's fine, and that's correct. But now let's just give a substantial answer. Why are you doing that? To get rid of C, I guess is one way to think of it. To get A by itself, yeah, sure, you can think of it that way. To isolate A, take it out of this big conjunction so that it's alone by itself. But why do we want to have A alone? So that we can then use biconditional elimination on 1 and 3, exactly. The pieces of a derivation in logic are like the pieces of a puzzle. Each new step opens up new options for further steps. I mean, like in video games and stuff, like if you play games like this where you get an item, now that you have the item, it's like, what can I do now that I have arrived at the point in the game where I have this item? This gives me new options with which to advance further in the game. And so once you've got A, your mind has to start thinking about critically, what can A be used for? There's a reason that it's in the proof now. And you see, by comparing it against line 1, that it eliminates the biconditional. So now we have D and W, biconditional elimination, 1 and 3. And so that would be the proof of this problem. Okay, just giving you guys a little bit of work on the biconditional elimination. Yeah, and then, I mean, I guess I could also do one more practice problem along these lines. Like, suppose I had D and W and X. And the goal is to derive just A. We'll just do one more of these before I show you disjunction introduction. But what would you do here if you see this problem? Tell me, what do you think you could do to take this problem to the next step? The goal is A, ultimately. So looking at the problem, you want to get to that outcome. Okay, Frida, so you say D and W, and that comes from conjunction elimination of line 2. Yes, because line 2 is a big conjunction where the left side is itself a conjunction and the right side is an atomic sentence letter. So we can remove this component from the conjunction because this is its main connective. Thus, we take off D and W. What's line 4 then? What's line 4? And keep in mind, yet again, we're trying to ultimately arrive at A as the last line. So what is the next step? On line 4, we only need one more step. Good, Nathaniel, it's just A. But yes, and the result is derived from biconditional elimination of 1 and 3. Line 1 is where we have the big double arrow statement. Line 3 is where we have the right side of it. And with double arrow elimination, we can eliminate from left to right or right to left. So the combination of 1 and 3 produces A, which is the goal of that proof. Okay, so then let us go to the next connective inference rule. So what we're looking at now is, here you see on the share screen, disjunction introduction. And the symbolism that denotes that is wedge I. Okay, so disjunction introduction. Here's how this proof, or sorry, inference rule works. Suppose that within a proof you just have anything, like the letter P. Okay, well, I have to, I think, explain the logic behind this just a little bit. Think again about what is a disjunction. Tell me, what type of sentence is a disjunction sentence in English? Just in everyday English, common sense. What kind of statement is a disjunction, if you were to describe it in more everyday language? A disjunction is, in other words, a what type of sentence? Let me know. It's an or sentence. Good, Lily. Conjunction is an and sentence. Disjunction is an or sentence. So can you give me an English example of a disjunction? Just a statement which has or in the middle? Just throw out one so we're all able to focus. Well, apple or banana, okay, but that's not a complete sentence. There we go, Isaiah. I will eat pizza or ice cream today. It's an either or. It's about what you're going to eat, I guess. Although it's a strange menu of options, my friend. Ice cream or pizza. I mean, they're both, anyway, but that's fine. So you'll either eat pizza or ice cream. Now, how many of the two disjuncts have to be true in order for the whole disjunction to be true? So like if I say that I'll eat pizza or ice cream, what number of those things have to be true for me to speak something true? Yeah, exactly, 1. If I say I will both eat pizza and ice cream today, that would require both. But no, Frida, with a disjunction, it only requires 1. Because when you say or, you're not saying both. You're saying just one or the other. Like if I told you that Trump or Biden will lose the election, that doesn't mean that they'll both lose. It means that at least one of them will. Okay, now if I say they'll both lose the election, I don't know, that would be like Kanye wins or something like that. It's not going to happen. But saying they will both not win is way different from saying that either one will lose or the other will lose. Okay, so since only one member of a disjunction has to be true for the whole thing to be true, if we know that one statement is a fact, that implies that either that statement or anything else. Okay, so like for example, am I wearing glasses right now? Is that true? You could just tell me. That one I think should be pretty easy. Just let me know if you're watching this video. Okay, good, I'm wearing glasses, it's a fact. So is it also true then that either I'm wearing glasses or aliens exist? Is that statement true, that either Vulic is wearing glasses right now or aliens exist? The or statement. Yes, it's also true. Why? Because I don't even have to know the truth value of the second disjunct. Knowing that I'm wearing glasses is enough for the full disjunction to be a fact. Okay, so like, I own 2 cats. So therefore it's true that either I own 2 cats or the moon is made of cheese. Because the fact that I own 2 cats suffices to provide truth to the statement when it's an or statement. Okay, and would require both. Somebody's mic is on, so just take a look at that. I don't know who it is, but and would require both to be true. But or requires that at least one be true. So from one fact, I therefore am free to disjoin anything to it. It's kind of weird, but if I know that some statement is true, I can disjoin anything that I like to it. So when I have P, disjunction introduction allows me to write P or Q for any statement Q. Q could be an individual sentence letter. It could be a big complex formula. It could be any well-formed sentence in logic. But I can disjoin anything to the letter P or to any sentence that I have by means of disjunction introduction. Okay, and one other thing about disjunction introduction, I'll show you this. Suppose that I had a formula that looked like the letter P. I can also use disjunction introduction to disjoin something to its left. So I could also make the additional material the left disjunct rather than the right. So from the fact that Trump is president, it follows that either Trump is president or there's water on Mars. And it also follows from the statement that Trump is president that either there's water on Mars or Trump is the president. So the placement of the one disjunct that we add something to, it's irrelevant whether it be on the left or the right. That's all that this is showing you. So the additional info that you introduce by adding the disjunction symbol and placing some content either to the right or the left, it's fair to have it on either side. Okay, so now we've learned a little bit of additional information about disjunction introduction. Let's see how this works in a problem. All right, so suppose I tell you to do this. Derive A or B and C. And all you're given is this one assumption, which says A. How to do it. Knowing this rule, hopefully you'll just think of it won't take too much time or be too difficult, but let me see what you think. This is what you got to get. All I've told you is A. So what inference could be done on line 2 to just give us our answer? Let's see. What's the inference? Big hint, it has to do with what we are just now learning. So you've got A. You need to get A or B and C. Okay, so Frida, you say to write, Lily, you say A or B and C, disjunction introduction of 1. That's correct. Now, Frida, writing just the letter A is not the result of doing disjunction introduction. Because with disjunction introduction, the result of using the rule is some sentence which is a disjunction. You're introducing a disjunction into the proof when you use that rule. So it will never be an individual letter like the letter A. It's always going to be a formula of the form something disjunction symbol, something else. And Lily, you have it. A or B and C. Disjunction introduction, line 1. This is the whole answer. What did we do? We added everything on the right, B and C, to the single letter A. Disjunction introduction allows you to do that. It allows you to add whatever you want to either the right or the left side of an existing statement. So since A was made available, we can disjoin everything else on its right. Suppose that this is the result we need, A or B and C. And the assumption instead, in this case, is that B and C. How can we get to the result now? Similar question, similar answer. Let's see. What's the inference now that takes us to our outcome? The desired result is this big disjunction of either A or B and C. And what we know so far is that we assume B and C is true. So how can we build up the full statement then? It only takes one step. And it uses the same rule. So Isaiah, A or B and C from Disjunction Introduction on line 1. Good. There you go. In this case, we had the full conjunction, and we simply disjoined to its left the extra symbol, the extra sentence letter, to get the result. So with Disjunction Introduction, you can add a statement of whatever complexity to either the right or the left of an available sentence. You'll just disjoin them by means of the wedge connective, and you'll place it on either the left or the right as needed according to the needs of the individual proof that you're working on. Okay, so now we're going to combine some of these rules and go back to our problem set to work through a couple more of these problems. All right, so let's try problem C right here. Okay, so we've got a whole set of inference rules. Let me just remind you of the names of them all over here to the left, and then we'll go through this proof together in the order needed. So we're looking at 5.1.1 problem C. Overall, here are the inference rules that we know of so far. Conjunction elimination, conjunction introduction, conditional elimination, biconditional elimination, disjunction introduction, and then the reiteration rule. Okay, so both of the conjunction rules, the two conditional elimination rules, conditional and biconditional elimination, disjunction introduction, and reiteration. So we have 1, 2, 3, 4, 5, 6 rules for now. We're not going to be using reiteration just yet, though, so in a way, there's only 5 that you need to think about for the moment. And this is our problem, problem C. Problem C says to derive this. Derive, it is not the case that A, if and only if, not B. All right, and in the proof, we start with these 3 assumptions. So assumption, assumption, assumption. The first assumption is a big biconditional. It says that not A, if and only if not B, not the case that A, if and only if not B, just in case either not C or not D. Okay, so let me make sure this is easy to read. And that's clearly a tilde. All right, that's the first premise. The second premise says that if A, then in that case, both not D and C. And the third assumption is that both D and A. Okay, so from here, you have to just, with each new inference, add a new sentence to the proof, and in the justification column, just cite the justification for adding it, meaning that you have to cite the rule that you used and the relevant line number or numbers that gave you the ability to create that new line. So on line 4, what is something that can be done using the available rules and these 3 statements that are above? What is something? Okay, so Frida, you say to give A from conjunction elimination on line 2. Good. That's a good idea. That's a good starting move. Notice that by doing that, we now have access to the letter A disconnected from this conjunction. We've stripped it off of this by using conjunction elimination. Wait, sorry, line number. It's 3. I meant to say 3. If we made an error, I'm sorry. Yes, Evelyn, it is line 3. I did not mean to misspeak. Line 3 is where the conjunction is, and we have removed one of its 2 conjuncts. So it is 3. Conjunction elimination on line 3 gives us A. So what, though? Now that we have A, you should think about what could be done next. So what can follow after from having the result A? You look back at the proof with every new line that you add, and you consider what this new addition can do in the light of what is already available before and the inference rules that we have. So now with A on the table, we get the option to take another step. What could that next step be? And the hint is that it's involving A. So let's see the next inference in this proof. There's really only one thing that can be done, to be honest. There's only one possible option. So you'll see it. What is it? The next inference, line 4. Okay, good, Frida. You say D, not D and C. And that is on the basis of conditional elimination using line, let's get the numbers right though, please. It's lines 2 and 4. Okay, good. Tilde D and C. That is conditional elimination line 2 and 4. Does this step make sense to us? Can we all understand that? Where is this coming from? It's coming from eliminating this conditional here and getting the stuff on the right. Conditional elimination always works in this way. You have a conditional on one line. You have the antecedent of it on another line. Using those 2 parts, we get just the stuff on the right. And that's what we have here. So like once you eliminated this conjunction and got A, your mind should have started thinking, well, what can A be used to do? A cannot do anything with this, nor can it be involved in this because we don't have a full statement that is one of the 2 biconditional statements. But look at line 2. A is the antecedent, so that should have caused your mind to figure that these 2 have a relation, and they do. It's the relation of conditional elimination. But we're not done yet, because ultimately what our goal is going to be is to get to this biconditional statement up here. Well, sorry, this negation of a biconditional. So what about line 6, you think? Where can we go next in line 6 to take us to what we're trying to get to? Now, can we all look at something? What's the result we want? It's this. Where does this statement appear in the formula, the thing that we're trying to derive? Where does it appear, sorry, in the derivation? It's in line 1, correct. It is the left biconditional statement in this big biconditional. So if we can get this side, then we can use biconditional elimination to arrive at our goal. So anyway, that's a hint. What do you suggest that I do next in this proof on line 6? There's only so many options given the material that's in the derivation. But I need you to tell me, what's line 6? What is line 6? Do I hear a microphone? Someone's speaking? If so, it's fine, but let me know. Anyway, though, what do you say? Line 6. Line 6 of this proof. The next line. Even if you don't know where you're going, you can tell me a rule, even if, as long as it can be applied. Okay, so Lily, you say negation of D, not D. Take that out of line 5 by conjunction elimination. Very good. And that's conjunction elimination of 5, correct. So look at line 5. Line 5 is a conjunction. Every time you see a conjunction, think, should I eliminate it? Should I take something out of it? If you can, I would just say exhaust all possibilities and just do it just because you can. Well, anyway, here's not D. We're still not at the ultimate solution, but we're making progress because not D is like half of this disjunction that's buried within the biconditional here. And that's a big hint as to where we go next. So what about line 7? One of our new rules is going to come into play now in this proof. So Lily, you're saying not C or not D from disjunction introduction on line 6. And that is correct. Okay, so do we understand this step? This step line 7. All we did was that since we have not D on line 6, we can disjoin to its left whatever we want. And since we want this statement, which is a disjunction, we choose to disjoin to its left tilde C. Now we have this big formula, which is a part of line 1. And that means that we only need one more step now. So what about line 8? What is the inference to do for line 8, which closes the proof? That's my question. The final step. Look at the information on line 7, and if you scan back to the previous lines and think about our inference rules, you should see what the next and final step is. If it's the final step, that's also another hint, because the final step always results in writing the derived result in that line. So what is line and step 8? What is the 8th and final line of this proof? It's not a mystery. It's quite clear. What is it, though? I'll never tell you. You have to say what it is. What is the last step? Evelyn. Okay, good, correct. But what's the inference that gets us there? What inference rule allows us to write that? Okay, very good, Arlene. It's biconditional elimination, 1, 7. Exactly. And there we've proven it in 8 steps. So looking at the proof one last time, and here, let me pull up the solutions manual on that. This isn't the one, though. It's this one. So yeah, yes, I'll explain. So line 7, where does it come from? It comes from disjunction introduction. The rule of disjunction introduction allows you to disjoin any statement to the left or the right of an available line that's already in the proof. So line 6, Evelyn, is tilde D, which came from conjunction elimination of line 5, where it says tilde D and C. If you remember, we can take an individual statement off of a conjunction using conjunction elimination, so that's where tilde D comes from. Once we have tilde D on line 6, we can use disjunction introduction to add whatever we want, anything. We could have put like 100 letters here on the left of that. So yes, you can just add anything. 100% Evelyn, yes, you can just add it, anything. And since you have not D, all the rule says is you have to keep not D in there, but you can put whatever else you want on either the left or the right of it. So when you look at the biconditional in line 1, and you saw that tilde D is part of the disjunction on the right half of it, you could think that if I ever arrive at tilde D, I can disjoin tilde C to its left, as we've done here, and then use that full statement to eliminate the biconditional, giving us our result here. So seen on the board, you see our 8 steps. Seen in our screen share on Zoom, you see the nice typed version right there. Okay? Any other question? Very good question, Evelyn. Anybody else have any questions about this problem? I know that sometimes it's hard to even formulate a question because you're learning so many concepts at once, but please struggle to ask me questions if you have to, if you must, because you should. You can't leave things ambiguous in your mind because they will come back to haunt you later when you have pressure to do it correctly and you're like, what was the rule though? I still kind of don't understand it. So practice makes perfect, and we're going to have a lot of practice. But just get into that habit. It's nothing scary or intimidating. We're just working with logical reasoning, something that you already do all the time every day. without thinking of the precise rules and terminology associated with it. Okay, so that's question C. So I want to go on and let's try another one. And that's going to be this one here, problem E. Okay? Yes, more examples like this one. Very good, Brenda. We're going to keep working on problems of the same kind of complexity. So very good. All right, so now let us try a problem in the book. It's labeled as 5.1.1, letter E. Sorry, I'm trying to get to the right page. Yeah, so that's the one that you see displayed in the chat. And there are 3 assumptions again. Here's the derived goal. Derive the formula if F, then not G. And we have these 3 initial assumptions. Assumption, assumption, assumption. The first one says that if either E or H, then in that case, if F, then G. Sorry, if F, then not G. Okay, and the second one, C or D, if and only if, double arrow, if and only if both E and not H. And then the third, C, just a single atomic sentence, C. Okay, so we have work to do now to get ultimately to this goal. So let's take stock. Sometimes you want to examine and scan the whole set of assumptions and the goal before you even make your first move. Here's the goal, what you're told to derive. Does that statement appear anywhere in any of the 3 assumptions? If so, let me know where, in what line, does the derived result appear. It's in line 1. Okay, good, Isaiah. Where is it in line 1? Well, it's at the tail of this arrow. So what inference ultimately could perhaps get us that result if we could find another part of the sentence? In the end, perhaps the last step of this proof will be to do what? Think logically about that question. You see that the goal sentence is a part of line 1. What is a rule that can be used on line 1 that can ultimately release that statement that we want to derive? Which inference rule can break down line 1 and give us the statement F arrow tilde G? Like, I'm asking you to kind of think in advance of what the ultimate final step of this proof will be, because that'll give you a sense of what intermediate goal to get to. That's how like logical inference and reasoning works. You have a major goal, that's this. But then there are like some sub goals along the way. Like to get to that result, you have to first get something else before it. But I'm not getting the answer yet. Answer my question, what is the inference rule that is going to be used to get F arrow tilde G in the end? Yes, it's going to be conditional elimination. And if we're going to do conditional elimination, then we are ultimately going to have to get what other sentence before we can eliminate line 1. As a stepping stone to doing conditional elimination on line 1, we will have to first obtain what other part of the statement, E or H, okay? So keep that in mind. If we can somehow get to E or H, then we will be 1 step away. So just a reminder. But anyway then, let's start the proof. Line 4. What is something that we can do on line 4? Limited options available right now, because you cannot eliminate either of the conditional or the biconditional yet, since you don't have any statements available that are on the left or the right side of either one. So then, good Arlene, you say C or D, but what's the inference rule to get us that? Okay, so I'm a little confused, but yeah, okay, good, Brenda. C or D is from Disjunction Introduction on 3. Look at line 3, it just says C by itself. Disjunction introduction gives you the power to disjoin whatever you want to it. So why are you disjoining D to it? Why did we do C or D? That's correct, yes. But why though? Why did you choose to introduce D to the C or D disjunction? What was the point of doing that? You must have thought, Brenda and Arlene, that there's a reason to specifically add D on the right. And you can tell us what the reason is so that we can go to the next step. Now that you have C or D, what was the reason? What was the point of that? Because if you have C or D, then what happens next? It is in the second line, correct. So tell me then what the application of it will be to the proof. It allows me to add on line 5, what next step? The presence of C or D opens up new options. Well, we wouldn't say disjoin, but yes, so that we can eliminate the biconditional statement. And now that we can do biconditional elimination, what's the product of that on line 5? Line 5 shows us the result of biconditional elimination, yes, but just give me the sentence that I should enter on line 5, and then the justification plus the lines. So we got it all there. It's all, put all these pieces together and just tell me how to complete line 5. Okay, so you have E and not H. And the rule was biconditional elimination, so double arrow E, of lines 2, 4, exactly. Line 2 is the big biconditional. Line 4 contains the left side of it, which we built from line 3. Now we can eliminate that and give us this on the right, which says E and not H. E and not H is great, but it's not exactly all the way to our goal yet, but it's getting us closer. Using this, think about what is the following step to enter into the proof. Step 6. What do you believe can be added on line 6? Okay, so just E. Good job, Lily. E is the result of detaching that from line 5 using conjunction elimination of line 5. So now we have E. And that is another helpful statement, which is taking us closer yet again to the final result. With E, what is to be done next? From E, we can infer, using a derivation rule, a next statement, E or H, yes. With E or H, what's the rule and line number? It is disjunction introduction of line 6, correct. So we simply added onto the right of line 6 this statement H. Why would you do that though? Why do you want E or H? You told me to write it, so you must have had a thought in mind. What are you going for? You have E or H. What's the point? Yes, it is for conditional elimination. And specifically, what statement are you going to conclude here? On line 8. You got the rule. Well, yes, you have the rule to use. Right, F arrow tilde G. That's correct. If F, then not G. That, by the way, is the goal. So we're done, just have to cite the rule. And the rule is conditional elimination, line 1, 7. Line 1, where this big conditional occurs. If you combine that with just the antecedent clause, E or H, that eliminates the conditional and spits out the right side of it as an output. So from these two inputs, a conditional and its antecedent, we can derive this as an output. F arrow tilde G is the goal, and so there we've proven that. Here you can see it displayed in the screen share as seen on the board. So line 4, disjunction introduction of 3. Line 5, biconditional elimination of 2 and the newly available 4. E on line 6 is the result of conjunction elimination from the newly available E and tilde H. Now, with E by itself, noticing that it's one of the parts of this disjunction in line 1, we disjoin H to it, giving us the antecedent of line 1, which then allows us to eliminate the conditional, getting us our goal. So in another 8 steps, we have another proof of that problem. Okay, let's continue. There's more to do in this problem set. So let's try letter G then, huh? Here it is, this statement. Or, sorry, problem, derivation. See, a statement is just one of the things in the proof. So to speak precisely, you know, the derivation or the proof. Okay, so letter G now. And the first thing, again, to always look at is what's the goal. The goal of this one is derive D if and only if double arrow not B. D just in case not B. And here are three premises of the argument. So to start off, if both A and not B, then in that case, C. Okay, let me make that a little cleaner. Sorry, the right parentheses was just a little too tight. Give this letter B a little room to breathe. Yeah, so that's one of the assumptions. And then the second one is that if either C or D, then in that case, D, if and only if not B. Okay, and then the third premise of the formula or the problem is both not B and A. Okay, so ultimately we got to get here, but we're starting with that. So I can already sort of see a few things to do here, but what do you think? What would be your first step in this proof? Yet again, you should kind of look more at line 3, because line 1 and 2, you can't really do anything with them until you get like one of the formulas on either the left or the right of those connectives. So your attention should draw towards line 3 and start making some basic inferences. So what do you believe maybe we should start with on line 4 here? Just one of our inferences. There's not too many options, so you have a narrow range of options. What is line 4 of this proof? What do you think? I mean, like, so remember, you got to be patient with yourself with these proofs. I think sometimes a student is like, well, if I can't solve it in one step, and if I can't see like the 4 or 5 steps ahead of me, I just am lost. But you kind of have to sometimes just go blind. Like, even if you don't know how it's going to get you to the end, just do an inference. If it's an inference that's a valid inference, just apply it and just see what happens. So try something. What can be done on line 4? Okay, good, Isaiah. Conjunction elimination, give us A. Conjunction elimination of line 3. So we have A. Not yet maybe exactly clear what we're going to do with it, but we have something, at least. Something's better than nothing. But we're not done at all. So what's the next thing? What's the next thing? That was good, though. That's exactly correct. Disconnecting A from the conjunction is the right way to go, but there's more to be done. Arlene maybe meant to say, I think I know what you mean, but just maybe you got to rewrite that in the chat. Tilde B. Yes. Now, good, Brenda, but what's tilde B coming from? Let us know the rule. That's correct, but what rule again? Yes, conjunction elimination of 3. Okay, good. Okay, so we had some things that we did not have before. These two things placed by themselves on separate lines. Okay, wheels are turning in your mind. Now you're like, okay, I see something that can do. Maybe you can just tell me what it is then. With these two things, what can we add to our proof? We can create something that will take us to further steps. So just who sees it? Once you see it, just go ahead and throw it out there in the chat, and we'll add it to this proof. Look at the above lines. Okay, good, Arlene. You say connect A and not B in that order. Right, so we basically had to take this apart and put it back together in the proper order so that it will be the antecedent that you see here. That's A and not B. Conjunction introduction on lines 4 and 5. Very good. Sorry, line 7. But, you know, we still have more work. We have A and not B. So something very clear, I think, should occur to you now, what to do with A and not B. Look at all the above lines in combination with this new line, and then ask what goes next. Okay, Arlene, good. C, the result of conditional elimination involving line 1 and 6. Okay, we've got C, and we're getting close now. A couple steps, and we'll be there. What do you believe should be step 8? What can that possibly be? Step 8, you've got C now. C is giving you another option that you didn't have before you had C. Okay, good, Arlene. C or D. That's going to happen by using Disjunction Introduction on line 7. But what's the reason, though, for getting C or D? Well, that's true. Yes, you want C or D, but only because once you have it, you then can infer what? C or D, last step. It is the last step. And therefore, there's only one possible answer that it can be. What is the sentence and what is the justification? We've reached the end. Now, let's just close this one out. Tell me then how to finish this proof on the 9th and final line. Okay, good, Arlene. The result is D and not B. But give me the correct line citation, if you could. Wait, no, sorry, actually. Sorry there. Let me just double check what you have written. You said D and not B. Wrong connective, though. I hope I have not made it illegible to you, but you can see in the proof written in the chat also. Let's correctly state what proposition this is supposed to be here. Almost. Just got the connective a little off. It's not D and not B. It's what? It is D double arrow tilde B. You see also, Arlene, it's negated. This is a tilde sign. So it's just this. And that is the goal, okay? And the result that we got to is from conditional elimination, and it's line 2 and 8. Okay, so does this make sense? I just, small correction. I think you saw this as an ampersand. But anyway, C or D is the antecedent of line 2. Once we obtained that antecedent, we could eliminate this formula and just get the consequent on the right, which is, after all, the goal. Okay, so here we see the full typed out answer in the answer key. 4 comes from conditional elimination on line 3. That's letter A. Tilde B in line 5 comes from just removing the other conjunct, a second application of the same rule on that same conjunction. With the two elements detached, we can recombine them in the proper order to form A and not B. Then that eliminates this conditional, resulting in C. C then can freely be disjoined on the right with the letter D, which builds this antecedent here. And then we eliminate that conditional using this disjunction, giving us that consequent, and then that's the solution of the problem. So here's another one of our proofs using all the rules that we've so far learned. That's question G. Now let's see, maybe one more with a little bit of time we have left. If I could just run through it kind of fast, then that'll be a good thing. So sorry. Okay, so let's try to do this one real quick. Letter F. Okay, what it says is to drive is not G. And you're given these statements to start us off. Yeah. If H and not I, then in that case, not G. And the second assumption, Either F or not G, if and only if. If and only if H, another assumption. And then third, right here, third, both F and not I. Okay, so lightning round. What do you guys think? Step 4, any idea? Step 4 of this one? Just something that we can add to the problem. Only one of the things looks like we can really break it down for the moment. So maybe that's a hint. What do you suggest? Where do we take this on line 4? Line 4. Just throw it out there. Correct, F. F based on what? What's the rule for that gave us F? Conjunction elimination 3, good. Okay, F came out of line 3. We eliminated this conjunction, and now we just have F. Okay, now keep in mind, what's our goal is tilde G. Where does that appear in the assumptions? It's on line 1. It's the consequent of line 1. So thinking about that, a probably sub-goal, an intermediate goal, is going to be to get this, at which time we can eliminate the conditional, we'll be one step away. But we're starting so far, we just have F. So where do you feel that we can go in the next step? And think ahead, don't wait for me to ask a question. If you already feel like you're judging in advance what the next inference is, then just go ahead and put it in the chat. So F or tilde G. That's based on the rule of, tell me the rule. Arlene, that's good, but just the rule we need to know. F or tilde G, yes, and it's disjunction introduction off line 4. Line 4 just says F. With the disjunction introduction rule, we can disjoin whatever we want. If we're looking for a disjunction and we have one of the two sides of it, then just disjoin the other side as you like. So that's disjunction introduction on 4. But why did you want F or tilde G? You must have had a reason for that. So the reason is because now you can do what? To go on to step 6. F or tilde G is important in getting us to that step 6. Because the step is to do what? Sometimes you don't want to think about the big picture. Sometimes you just want to think about the next step. And in this case, the next step is going to be to get H. Because line 2 combined with 5 can biconditionally eliminate this and give us H. Okay, so that's biconditional elimination 2 and 5. So if we have H, a couple steps we still need to take, and we're making our progress towards that. So what do you say next on line 7? We have H now. That's good. That's good news. But there's nothing we can do with H until we get something else. So, Lily, you say not I coming from conjunction elimination of 3. Correct. Notice line 3 has 2 conjuncts. We already removed F. That's where this came from. Now we've chosen to take the other side, I, off of it later. And good. Now that you have tilde I, there's something that follows next, which gets us right close to the end of the problem. What's next? I mean, you took tilde I off of line behind doing that. What could it be? Okay, you say H and not I, Arlene, by introducing 6 and 7, conjunction introduction. Good. All right, so we're there. We're at the end. Just got to finish it up. So what's next? The final line is line 9. What is the inference then? Tilde G, good, Lily. And where's it coming from? It is coming from conditional elimination of line 1 and 8. So there, 9 steps, we see this proof. And written in the chat, here it is. Same thing, derive not G. F proceeds from line 3, which is conjunction elimination. F or not G is by disjunction introduction from line 4F. Now that that whole formula exists, we can use biconditional elimination to obtain H. Now that H exists in the proof, we can disconnect tilde I from line 3 by means of conjunction elimination. And with those two sentences available on line 6 and 7, they can be conjoined on line 8 to form H and not I. And now with this statement on the table, we can use it to eliminate the conditional of line 1. That gives us tilde G. And that's the proof here in 9 steps. So, you know, if you just take it step by step, sometimes the next step that follows only becomes clear to you once you get there. So I think sometimes students can get like frustrated by trying to think of all the steps at once or something, or like, how do I get to the end? You know, be patient with yourself. When a new step is to be added in the proof, just focus on that one step, but then look back at the ultimate goal and keep in mind how you can add something to the proof, and also how the addition of each new line may make available new options when you consider the previous available lines, the inference rules, and the result that you're trying to derive. Sometimes there may be sub-goals on the way towards getting to your primary goal in the proof. The primary goal is always the sentence to be derived. But when you look in what's available, if you see that that goal sentence occurs somewhere, then you may then recognize that there is a prior goal that has to be achieved first. In this case, that is what we see. Because tilde G is the ultimate outcome we want, knowing that it's the consequent of a conditional should allow you to think that perhaps conditional elimination will be the ultimate step. And now your goal sort of becomes to find H and not I. And since you know you need H and not I, you know that there's some type of conjunction introduction rule involving other sentence letters that are available in other of the premises. All right, guys, so that's been our meeting for today. We're just learning a couple more inference rules. The main thing today was biconditional elimination and disjunction introduction. When we come back next time, we'll learn the last couple rules, or at least 2 more, and we'll just continue to build up our skill in doing proofs. So thanks again, everyone. I'm going to stop this Zoom feed, and then I'm going to stop the YouTube feed. As always, feel free to go back to watch the YouTube lecture at any future time. And check your announcements later today. I'll be telling you that the midterms are ready, and you can always check in with me for your score. I just want to create the answer key for that, and I will do that this afternoon. Okay, guys, have a great day, and take care. See you next time. Okay, signing off of Zoom. And then signing off of the YouTube. All right, guys, goodbye, and I'll see you back on Wednesday. Let me know if there's anything that you need. Take care.